All right, I'd like to clarify a few things about the Dragonfly Project. And I wasn't sure when I'd be able to do it because I have a lot of kids absent, and some of you talked me into giving the test on Friday. So there could be people testing today, on Thursday, and tomorrow on Friday. So here we go. I'm going to say it once on the video. You are responsible for anything I say here and now. Okay, so the way this works is, well, the story was I was sitting on my front steps and watching a dragonfly one day. And I noticed the different lines that he was kind of traveling through in space, and I, anyway, turned it into a project. So yay, you're welcome. Okay, so I researched it, and I found that dragonflies can fly at a speed from 27 feet per second to 54 feet per second. So what I would do, if I were you, is I would keep everything in terms of feet and seconds. And what this tells you, though, is the fact that they can fly at a speed of that means that your direction vector has to have a magnitude somewhere between that. Okay, so if you remember back to if you have your equation x, y, z equals, and you've got a position vector, whatever that is, plus t times your direction vector, the magnitude of the direction vector, this part right through here, that magnitude would need to be between 27 and 54. Also, okay, let me keep going. And it said the next thing, the dragonfly stayed in an area of at least 10 feet above the ground, and then I'm encouraging you to restrict his movements to a prism. Over the years, I have discovered that's easier said than done. So I am less concerned about this part right in here. The only definite restriction is that the dragonfly is not able to burrow into the ground. Okay, so it shouldn't go like 2 million feet away because he was kind of in this, as I sat there watching him, he was over the street between the houses or whatever. So, and he didn't go, he kind of stayed in the same local area, but I do understand that this restriction is rather difficult. So what I would say would be the z values must always be positive, and even the 10 feet above the ground, sure, do that, don't do that, I don't have a strong opinion. The only thing I have a very definite strong opinion about is that he cannot burrow into the ground. Okay, so then the next thing, the dragonfly may turn in any direction, but only may form a right angle once. So you can have him to make a right angle at one point, but then at one time in his trip, but the rest of the time, the angle shouldn't be a right angle. And it says he never retraces his path, but he does cross a previous path exactly once. Okay, so as he's flying, it's hard to draw on, but if he's flying here, he's turned and done something, and then at some point there is a point in common between those lines. Okay, this is not that little drawing I did is not accurate because that gave us what did it give us? 1, 2, 3, 4 lines, and I drew them all on the same plane, and you're going to find out in a second. Right here, every third path is non-coplanar to the two paths prior. So path 1 and path 2 will necessarily be on the same plane, but then this path 3 needs to not be on that same plane. Okay, so this is pretend that you can see that in a three-dimensional way, where this part right here has popped out and is going in a different plane. But then this line here, line 4, cannot be on the same plane as lines 2 and 3. Okay, then the math requirements. Write 6 equations of lines in vector form. Your equations should be similar to a piecewise function. Okay, so they're saying, for example, if the dragonfly changes directions 12 seconds after he starts flying, there should be 2 lines that give the exact same coordinate when 12 is substituted in for time. So back up here, where I have this t, that t value should be the same. You should put t in all 6 of your equations. And then at time, I should be able to decide, well, I want to know where he is 21 seconds into flight. I don't know why I picked 21. But then you'll tell me that this path here is defined like from 0 is less than or equal to t is less than or equal to 5 or 4 or whatever. And so then I'll look and you'll have equation 1 and then you'll have equation 2, and then I can look and see, okay, well, if on a particular one he's there from 15 is less than or equal to t, which is less than or equal to 27, I don't know, I would take that equation and plug in 21 for t and find out exactly what point in space he's at, okay, exactly where the dragonfly is. Okay, and continuing on, then we want, so that's, and that part right there with the 6 equations, that's what we're going to sit down together and check. And I'm going to type in all of your matrices into my calculator, and I'm going to verify that they really are at the same point at the time that you tell me that they are. So you're going to sit and make sure I type it in correctly. Because if I don't, it's very sad. So we're gonna work together on grading that. The next one, you have to write 5 equations of planes. So if we have 6 lines and the third, so like line 1 and 2 are on one plane, line 2 and 3 are on the second plane, line 3 and 4 are on the third plane, etc. So there should be a total of 5 planes, and I want the equations in vector form. Then find the angle he turns. So between any 2 lines, I want to find that angle. And it says give about 30 seconds of his journey that summer night. So if you decide for whatever reason to stop at 29 or go to 33, or, you know, I'm flexible on that. That's less of a concern than some things, but it should be about 30 seconds. Okay, so then find the magnitude of each vector and compare that to the velocity vector. So when I say of each vector, what I really mean is each direction vector. We want to know, I don't really need to know the if you remember, so here is xyz equals your direction vector, and then, oh, so sorry, that is not what I wanted to do. That pretend is a plus sign. Okay, and then here is your, position vector here, and then your direction vector is this part, the position vector is this one. Well, sometimes you might be at point, your x could be negative 15, and you could be at 437 and 139. I don't know. So I don't really care about the magnitude of this vector, because that's just telling you how to get to a spot on the line when t equals 0. So this part right here, the position vector, doesn't have a whole lot to do with what the dragonfly is actually doing. But when I say in here, find the magnitude of each vector, I'm talking about the magnitude of each direction vector, and then compare that to his velocity. So the magnitude of that needs to be between 27 and 54. Okay, and then we did say at one point that there were 2 paths that cross, and you need to find that point and show me the work behind finding the intersection. And then find the total distance of the dragonfly traveled, which is different from the displacement from where he was at the beginning to the end. Okay, so if you think about, I'm going to pretend that this is 2-dimensional for a second. If he goes 1, 2, 3, 4, 5, 6, right, is that 6 lines? Well, whatever, I don't really care. The total, the displacement at the end is from where did he start to where did he end. The total distance travels along this whole path. Okay, so that's the difference between these two. And this is a hefty project, I'm not going to lie. So it is worth a test grade. It's worth 100 marks, and we will be grading it together. So what I'm going to do is I've designed it's due on a Thursday. We'll talk about the calendar in a second. I've designed Thursday and Friday to be days where you can work independently on something else, and I will bring each group up over to my desk, and we'll sit through, and we'll grade it all together, and you'll walk away knowing exactly how well you did. It says it's due March 1st. I'm sorry, that's an old data, seeing as yesterday was March 1st. And I said you can work in groups of up to 3 people. So groups, you can do it by yourself, you could do it with one partner, or you could have a group of 3. I would prefer that HL stay with HL and SL stay with SL. But even that, if we have people that, it's a crazy time of year with a lot of absences. So we're going to do the best we can to make that work. Here is my thought on how the next handful of days are going to go. So you'll notice over here, well, I had intended for the test just to be on Thursday, but many of you talked me into allowing you to take it Friday, so I didn't change it on the calendar. But if you're testing in one of these 2 days, that's fine, but then that does restrict the number of days you have to practice or to get your work done. SL, the red is SL. SL has 1 extra day because I need to move on, and I'm going to work with HL. We're going to move into complex numbers, which is an HL only topic. SL doesn't do that. Because SL keeps it real. Okay, so it's due at the beginning of class the following Thursday. So, and then the next, these activities here, you'll be doing independently, and people will come up to me, and we'll sit and grade the project. So if there's any questions, come see me. I hope this clarifies a lot. If you don't watch this, oh, and then there's a rubric on the back of the page that I gave you. That's for me to write on, okay? It's you to check to make sure you have everything. But if you try and fit all the answers in that rubric, it's really small and kind of ridiculous. So do your work on your own paper, and then bring that rubric with you. So and definitely verify it, because you'll see how I'm weighting different things and how many points you get for different stuff. So come see me if you have questions. I hope this was helpful.